perspectives and the reasons behind it, and can perhaps come closer together in their conceptions of how the space should be structured. But because of different use cases, different perspectives, different requirements, different assumptions about the nature of the systems, I'm not sure that we can ever achieve complete consensus. So for instance, in your framework, the core of it was that we need to essentially constantly do field patches as the way to maintain constant safety.
Understand what's happening, and hopefully if we get the gap small enough, the monitoring most of the time will say it's fine, carry on. But if you were doing constant patches, you're in trouble. Yeah?
Yeah, I would agree with that. You would be in trouble if you had to do that. In some cases, if you have to do it quite a number of times, though, I mean, you've already failed. Because if the system is mission critical enough, is safety critical enough, is sufficiently leveraged and powerful, even a single mistake can be, a very large disaster.
Yes, I think that's right, but I also believe the idea that we can do the analysis in advance well enough that we're never going to have problems is unrealistic, and also the systems continue to learn in operation, then you need to continue to monitor them, to supervise them, to make sure they're learning in a direction that's appropriate, and if not, to take some control or corrective action, and I don't see how that's avoidable ultimately. I mean, you talked about oversight in your model. I see that as being, very much analogous with that.
Yeah. So I guess what I would say is that there are different levels of mistakes that can be made, and ideally you would have it learn on relatively low impact types of things, and eventually get to the point where, when it's being deployed for very large mission critical things, that you do have very high degree of assurance without having to sort of hoping, not hoping, but of having certain types of guarantees by the nature of how it was designed, that you would have a probability of not having a disaster.
Yeah, I think that's right, and you notice I'm not saying that you don't do the normal safety process, you don't do the normal verification, validation. You do. All I'm saying is that the evidence is that that's inadequate. I mean, and I've already said it isn't really adequate now for existing things. So let me just give you a little vignette. Some years ago I met the chief technical officer of Airbus when they just finished the A380, and I said to him, it seems to me that doing safety assessment of this aircraft is at or just beyond our ability to deal with complexity. And he smiled. Let's agree it's at the limit of complexity we can manage, which I interpreted as meaning he knew it was beyond what they could do. And that doesn't have any machine learning in it. It wasn't deliberately autonomous. So yes, we try extremely hard. If you look at the mature industries like nuclear power, like aviation, they do automotive, they do extraordinarily well, but they still get things wrong. And all I'm saying is that you actually need to make sure you have that feedback process from reality to deal with things that go wrong, which hopefully will be rare. But I say the more the systems learn in operation, I think the harder it is for us to guarantee that they won't go wrong at some point in the future. So I think we're saying compatible things but coming from a different perspective. If this happens often, then we've screwed up. If it doesn't happen at all, then we've done astonishingly well, far better than I believe we're capable of doing, given the state of the analysis techniques.
Right. I guess what I'm also saying is that we should engineer in some kinds of safety valves, where or pressure valves, where we start seeing problems earlier on before they manifest into larger problems.
Yeah, I think that's right, and my guess is that actually, again, machine learning might be very helpful in doing that. if you, some of the classic safety stuff that says for every accident you have, you maybe have 30 near misses, 100 or a few hundred, deviations from intent. And normally we only tend to monitor the accidents, but if you could actually work out causal structures enough that you could say, actually, there's a trend in these precursors which is in the bad direction. What do we do about it? Then that could be extremely useful. And actually, the medical example I went over very briefly, that's exactly the sort of thing that we want to be able to do with that, and actually look at trends in the medical data and say, actually, this is a disturbing trend. We should try to do something about it. So, yeah, I think you're absolutely right. For some things, it's very hard to do that, but where you can, I think you should. Mm-hmm. Yeah.
So let's jump back, sort of meta, or jump
Sure.
up. So, in terms of actually achieving consensus on a single taxonomy, which I think was, in theory, the nature of what we're attempting at in this workshop, and trying to address the challenges to consensus and doing that here. So do you think that's realistic, that the different perspectives can converge?
I think it is at an abstract enough level. At a detailed level, it may not be. I mean, I didn't show this, but this is the top level structure of our body of knowledge, which is quite a lot different from yours. It doesn't delve into many of the issues that you're talking about, but the blue bit is validation, as I said, by far the biggest bit. The green bit is essentially verification, but the orange-coloured bit is actually about dealing with deviations from intent, which is a very classical safety engineering thing, but actually I think is not incompatible with some of the things that you talked about. Then the green on the far right is about what you have to do in terms of regulation, but actually you could ignore that from the point of view of the taxonomy. This is much shallower than yours, deliberately, and it bottoms out on some of these, models of the machine learning life cycle and the way the system works, the monitor, analyze, plan, execute. So, it is structured quite differently, but I think you could probably agree a top-level structure. And I don't mean this in a pejorative sense, but in some senses what you've done, I think, is rather more philosophical. This is more oriented at actually how do we gather evidence enough that allow us to deploy the system. I think you could probably map those, say, actually these philosophical concerns are underlying issues that you need to address in some of these areas where you're trying to get assurance evidence, and maybe you could produce models that are consistent at the top level, are different in detail, but you could link them across, a bit like your yellow lines that you had on your diagrams. We could have some different coloured lines that go between the more engineering-oriented perspective and the more fundamental perspective.
Yeah, I mean, a lot of the content in mine is quite specific technical engineering techniques as well.
Yeah.
So it's really more at the sort of conceptual node splitting or conceptual hierarchy, where we place, I would say, both things that are more theoretical and things that are more specific types of engineering techniques. I don't see a need for two different types of landscapes there.
Okay, well, it would be interesting to try to do that, but I think we probably need to, if we trim the trees to 2 or 3 levels to start with and see if you could, realign them at that level, you could then go back and look at the detail. I think trying to do the whole lot at once would be pretty mind-bending.
Well, yes, I mean, this is all a lot of work, and I don't know that any of us actually have scheduled on our calendars to actually do this.
No.
But yeah, I mean, as you mentioned, with your orange area, that seems to be somewhat compatible with control, I would say, which is also looking for deviations from what you want to happen and
how you control that. Yeah.
Yes.
Yeah, indeed, and I think that is right. It's more actually understanding what could go wrong that you need to control, and the control would end up back in the requirements that you then validate and verify. So it's kind of structured rather differently, but I don't think it's addressing something fundamentally different.
right, and partially because of that loop, we have potentially different top-level conceptions of what various nodes should be and their ordering in that
Yeah.
hierarchy. Because really, I mean, we have a graph, right?
Yes.
I mean, fundamentally, it is not a tree.
Correct.
Fundamentally, it is a graph of many different types of relationships in a large ecosystem.
Yeah.
And even a single system has many different kinds of workflows that go into different versions of that system.
Yeah. Absolutely.
And so it is somewhat arbitrary as to what the actual structure of that tree is. Not completely arbitrary, obviously. There are important relationships, but
Yeah.
in terms of certain decisions.
Yeah, I quite agree. I mean, it isn't really a tree structure, and we've produced this particular structure to make it intelligible and explainable. And again, like you, if you look at the body of text, you see there are cross-references in various places that there necessarily are. You know, it's a wicked problem. There is no simple decomposition.
Mm-hmm.
Yeah.
And in mine, I did not have things like regulation, but I think that expanding the landscape, as it were, into things like regulation is something that was sort of in the scope of what this workshop was about. And I would say that actually there's an updated version of my landscape that was done by a colleague of mine, that built on mine, that also includes things in policy and things in ethics. And it's important to understand the relationships between various ways of analyzing ethical situations with ways that those analyses can be implemented in code by the actual AI systems, and with considerations in the actual design process.
Yeah.
I mean, there's so many different facets to safety.
Yeah, I think that's right, and I think it does also link to the regulation. I mean, there was some interesting talks about ethics yesterday, but you know, one of the complications is the regulators are often trying to take an ethical position on behalf of a much broader population. You can't make your ethical decisions yourself about your regulation of an aircraft. You know, the regulators do that for you. So I think some of the ethical issues play in that, and you know, there are trade-offs in that I think need to be expressed as well. So I think that would fit more naturally into that regulatory perspective. Yeah.
Can we take one or two questions from the audience?
Sure.
Yes. Actually, I believe there is consensus at the very abstract level.
Yeah.
And technical diversity is not a bad thing, because technical diversity leads to different approaches, innovation, identification of different problems and solutions.
Yeah.
Now, the issue is that if we see, I mean, I was quite impressed and amazed by the big landscape that you have drawn. And my question is, how much these branches can be in opposition, in relation with each other? Can we achieve some objective without actually endangering another one? Are these four things that we can do together? Are there some branches that we just have to drop out? And therefore, the question is, should we examine if there are some techniques that should not be applied at all? I mean, technically feasible. I'm not speaking about I'm speaking about issues that are technically feasible, but not desirable to achieve. For example, if you consider that there is a high risk that a system is going to provide a failure, to have a failure, then the technology underlying the system should not be used. For example, should we use machine learning for flying civilian aircraft? If we are not sure that the aircraft will fly in the same reliable manner as today.
want to comment on that?
Sure. I mean, I think I partially understand the question, although it was a little unclear. I mean, I guess what you're... So what I'd like to say is that for different kinds of instantiations of this, when we're looking at particular application areas, there certainly will be parts of this whole landscape that are relevant in analyzing that situation and parts that are not. One, I guess, aspect of this, which I would say broadly falls under validation, which gets to your last point, is that indeed there may be no acceptable instantiation of a system. There may be no acceptable architecture or design of a system that actually achieves your aims and also meets your safety requirements. And in such cases, yeah, the right answer would be not to create the system. And that should be part of this, you know, that would be part of the framework as well, yes.
No, I agree with that there may be some things that we shouldn't do, but let me just take a slightly different perspective with civil aircraft. Now, there are many modern civil aircraft that use a lot of composite materials. Actually, they had a huge amount of uncertainty about them. So what actually happened is they were originally used on very small components of aircraft, minor wing spars, things like this. They were carefully monitored. Actually, when they did maintenance checks, they went and actually looked at how these materials worked. And over time, they've been used more widely in aircraft. And over time is actually decades, if I remember correctly. I could imagine us doing the same thing with machine learning. Somebody wants to come to talk to me who wants to have a single pilot operation of aircraft where the co-pilot would be a computer using machine learning. Well, I hope they don't do that very soon, but there might be a great deal of merit in building this sort of virtual co-pilot, watching what things it does, you know, what it would recommend over a period of many years maybe, and you may be able to build some confidence that you can build something that's actually effective in, you know, managing and monitoring systems as an incremental approach. And I did talk earlier about regulation becoming much more incremental. I think it would have to involve a lot of non-operational deployment to build confidence in some of the technology. So it might be something you say, actually right now you can't do, but there may be a route to enabling it in future. But, you know, a civil aircraft with several hundred people, you know, without guys in blue hats at the front, I think it's a very long way off if it's going to happen at all.
So, to follow up on this, because this is a good example, in this case, you mean that we should certify the system when it reaches a particular level of competence.
Competence, yeah.
And so should we lower the level of competence that we accept so that the system comes to market earlier? There you have a kind of dilemma between time to market and safety rules. And this is a social discussion because
yes.
The example of the car, etc.
Yes.
It's exactly this.
Yes, it is. I mean, I'm not going to give you a definitive answer one way or another. I agree, it's a social discussion. I'd actually rather we had the discussion explicitly, because think about autonomous vehicles, we're effectively doing that experiment right now without actually having had the discussion about whether or not we want to do that. So for me, I'd rather have the discussion in an open way, and you know, it might be that these are, you know, I actually advise an autonomous vehicle company in the UK, you know, I'm saying this with some understanding about how these things work. You know, it might be we should simply conclude that these things are too mature really to be being deployed, and we maybe need to take a step back. And if you talk to Volvo, they say actually they may have made their ADAS systems too competent, and they're thinking possibly about reducing the level of capability of these systems. So, you know, it's a good question to ask.
Maybe we still need to take a little bit of break. So let's take a 10 minutes break.
Thank you all for being here today.